All right, let's give this a test run here as well. As you can see, we've bought a new camera, so hopefully things are a little bit more clear. This lesson is intended to kind of be a refresher course on trusses. I know we covered those a couple weeks ago, back before spring break, but I figured it'd be worth our time to kind of rehash some of that information as well. So what we're looking at here is basically we're looking to identify the next in our list of structures, which involves two force members. Now, the requirements for two force members are that the members must be straight, they must be pinned at the ends, and then the loads can only be applied at the ends of the member, okay, only at the joints. There can be no moments anywhere, and I can't have a force acting kind of out that direction if I want to. All right, so those are all no-nos. If that's the case, okay, then all of these are true. They're identified as a two-force member, okay. And then if that's the case, then all of the internal forces when I cut this member will end up being axial in direction only, right? Meaning that they could either be considered as, compression or tension, but there won't be any bending or flexural effects as we start to look at that, okay? Basically, there are no other internal effects. And if I know this, then I know that I don't have to worry about any unknown effects happening on this member, okay? So again, those are the basic requirements. Now, let's switch over and let me show you some basic information about trusses in general, okay, that we've kind of talked about, all right? I apologize for the notes, they're a little bit old, but the information is still true, all right? So the uses for trusses, as we've talked about, or the structures are basically consists of cylinder members joined at the ends, okay, and they're commonly used in bridges. Everybody's been over a truss, and if you've ever been into a Best Buy or a Walmart, if you look up at the ceiling, chances are those are trusses as well, okay? Typically the members are pinned, but not necessarily. Generally, they're very, very slender relative to some sort of connection that's being made, okay? This is the old gusset plate example that you see. This is when somebody says a truss, this is what they typically think of, the big train trestles that go over a river or something like that, all right? And so what I can do is I can take this basic object and draw a free-body diagram in this case, and again, I'm assuming that connection is a common pin and that these members are straight, okay, and if that's the case, and if all the loads are only applied at the joints, which is typically the way those things are constructed, then my free body diagram becomes something that looks like that, okay, in which all the forces are axial on these. Now, when I draw this free body diagram, again, it doesn't matter whether we assume tension or compression, because if I assume it backwards, we'll get a sign reversal in our equations, but we'll know that we'll be able to figure out what the magnitude of the value is for that. All right. Okay. Now we're going to define a couple of terms. I kind of pointed at this in the last part of the video, and that is that the tension member is basically an elongation. So that's where I'm wanting to take it and kind of stretch the member a little bit. Okay, that would be a tension, and then in compression, it would end up being kind of a pushing in kind of effect, trying to squeeze that thing down. All right. So, and this will become important for us as we have to try to define our directions relative to that, because I can't, unlike support reactions, I can no longer say that the force is to the right, because if you look at this tension member in this first case, here's a force to the right, that is a true statement. But if I look at the other end of the member, or the other end of the internal forces of this thing, you can see that it's acting to the left. Both of them are required to be tension, so we have to kind of change our nomenclature a little bit. So instead of writing, AY is 5 kips and it has an arrow acting upward, now I have to do something that explicitly tells me all possible cases. So that would be one little change in our thinking and in our approach. Okay, all right. Now, trusses are typically, as you remembered from any high school physics class that you took, chances are you've always heard that triangles are the strongest, and that's true for trusses more so than anything. There is an issue that won't be covered in this class that has to do with instability. In this case, if you had 4 members that were pinned together, and you can try this as an experiment at home, obviously there's no lateral strength to this thing. If I came and I pushed this thing over, it would just want to try to fall over. Okay, whereas if it's a truss, I can push on this thing in any direction, and it's reasonably stable. Okay, and so the forces get shared by all the members, so it becomes a very strong shape. So most trusses are typically some sort of triangular pattern on there. Okay. All right, now there are 2 different methods for us being able to analyze. Okay, and the first one is the method is called the method of joints. Okay, and this is probably the one that we covered previously. The other method is called the method of sections, and there's some definite advantages for this guy. All right, so let's talk a little bit about the method of joints on here. Let me see. Okay, all right, so basically, as always, the first step is always drawing a free body diagram. Okay, and then once you have a valid free body diagram, remember our Y's, self-weight, internal, support, and external, okay, and the definitions that go with that, okay. Once you have a valid free body diagram, you then, just like no surprise, as we go in and we start to write our equations. Now we have, sum of forces y, sum of forces x, okay, and then I also get the sum of moments guy, and it's not basically used, and I'll explain why that is here in just a second. All right, so if we take just a simple little truss example that we have happening here. Here I have a triangular truss. You can see the dimensions, 2 meters by 2 meters, 45 degrees. I've put a 500 Newton force acting to the right. Okay, and if I go through and I do my basic statics, which you all should know how to do by now, is that I should be able to come up with the support reactions. And in this case, I've got Cy as a roller being 500 Newtons up, Ay being 500 Newtons down, and Ax being 500 Newtons over to the left. Okay, it's a very, very simple mechanism. All right, the method of joint says is that you start with a joint on the system and you draw a free body diagram. So if I were to draw a basic kind of a circular shape and look at everything that's inside of that particular area on here, okay, I could go in and I could draw a free body diagram of everything that's happening inside that. In this case, it'd be a free body diagram of joint B. Right. And when I do that, I get this basic number. Because remember, in order to be able to draw everything that's inside of this shape, I have to cut it here and I have to cut it here in order to be able to reveal those internal forces. That's the only way they show up. When I do that, the free body diagram that I get looks something kind of like this. And this is the free body diagram for joint at B. Now, I don't necessarily know the directions. And in this case, I've drawn FBC as compression. Normally, I draw these things as tension, but just for the sake of this exercise, I didn't necessarily do that. But that's okay. So you can see I do include everything. And once again, I've cut the section, and now I go in and I do my Y's again, weight, internal support reactions, and external. The only thing that shows up in here are the two internals. And this is the internal force that showed up from cutting this vertical member over here. Okay, and then I have FBC, which is the internal force for the diagonal, which was from cutting this guy here. All right, and then so 500 Newtons acting to the right, and we're ready to go. Okay, and that's the valid free body diagram for that particular joint. Everything has to be in equilibrium. These forces, these two unknown forces that were not on the whole system, are now showing up because I've cut part of it out, and these are required to maintain the equilibrium of what I've cut out. Okay, so now when I do that, okay, once I have a valid free body diagram, we can go in and we can start to write our equations to that particular picture. All right, and they start to look something kind of like this. So just like what we did before, sum of forces x is 0. Okay, if I write my equations on this, I have 500 Newtons to the right, so that's a positive. I have minus FBC, okay, times the sine of 45. That's the horizontal component of this diagonal guy. Okay, and it's negative because I assumed by my sign convention I'm doing everything to the right. Okay, once I do that, I can solve for FBC being 707 Newtons. Okay, and when I do that, we found out that the math on this tells me that FBC is a positive value. Okay, this is where I got to be a little bit careful on why I typically try to assume things are in tension, but I didn't do it. And said when I get a positive value, what that tells you is positive doesn't tell you it's tension. Okay, it tells you that what you drew on this picture was correct. So as you can see for FBC, I assumed it was compression. See how he's pushing on this joint? Okay, so when I found out he was positive in this equation, it meant that that assumption was correct. And so that's why he gets a compressive force. So that member, diagonal member, is looking to get a little bit shorter. All right. Okay. And similarly, I can go then and write my sum of forces in the y direction. And when I do that, I get an FBC times the cosine of 45 degrees. So that's the vertical component of that diagonal. Okay. And then minus the FBA. Now I assume the FBA was a tension value. See how it's pulling on the joint. Okay. And when I do that, I'm going to get the math, and it's going to tell me FBA is a positive 500 Newtons from my equation. Well, in this case, the positive tells me that what I'm doing on FBA is also correct. Okay, and so in this case, he's a tension. So you got to be really, really careful that you watch those positives and then look back at the picture that you drew. Okay, so that's one of the reasons that we'll look to be a little bit more consistent in what we do and be able to assume things out. But in this case, positive was this guy. This guy is pulling on joint B. That's why he's a tension force as we start to kind of look at that. Now, what we've done in this, okay, is if I go through, we drew the free body diagram for one specific joint, and that was this joint B that was up here. That's the one that we just did. But if I look at the whole system together, you can see how everything's kind of balanced, all right? Here's joint B that we just drew, okay? But if I jump down to A, I would get a picture that looks something kind of like this. I get a force pulling on this member, okay, and I get a force pulling on this one. So I've assumed tension on both of these guys, and then AX and AY are obviously the support reactions that we have. All right, and so that's the picture that we've drawn here. We'll be basically going in and drawing a free body diagram around that joint, okay, as we look at part of our structure. Okay, when I do that on here, okay, I can draw the rest of these, and typically we don't draw all of them at one time, but I'm going to show you these because I want to show you how they kind of work together. on these kind of things, all right? So here I assumed that FBC was a compression member pushing up on this joint here. Well, to balance this on the end of the member itself, if I drew a free body diagram of the member, I would have an opposite arrow pushing on that because these two guys have to be in equilibrium. Okay, and then if I'm pushing on this one, then along the line, remember, now this force is acting down the line of the member, okay, then this one has to be here to balance the guy that we just added here. Okay, and you can see how it was this direction, it flipped, and then on the other end of the member, it flipped again. And then by a likewise statement, we can say then that in order to balance this one, I have to add the opposite internal effect of what's pushing on this joint here. So that's why this force FBC is pushing here, but he's also pushing here. And again, that's why we have to be explicit in how we're calling tensions and compressions instead of just absolute up arrows or down arrows or those kind of things. And we can play the same game over on this one. All right, here's my joint A. Here's AX, we assume to the left. AY acting down. FAC was assumed to be tension horizontal. This guy was tension up. And again, this is the balance because here we assume tension on this one. It flips to acting up this direction, and then it comes down, and then it is balancing. The member has to be balanced. Everything has to be in equilibrium again. And then when I do that, I come down, and to balance this guy, I have to have an arrow up on this joint here. And that's the way all these kind of construct together, and then likewise across the horizontal. Okay, so once I have that, now I can come in and I can start to draw some of my basic equations. All right, now the actual equations themselves are very, very simple. Again, for this joint up here, I can write sum of forces X, I can write sum of forces Y. Okay, FAC minus, for FX, I'm assuming that to the right is positive, so FAC minus AX is 0. So here's the positive FAC. Okay, and I'm subtracting off my AX value, which we had from when we did the original free body diagram. Okay, and so we find out that FAC is a positive 500 newtons. Okay, and when it comes out as a positive, then the positive value on this tells me what I drew is correct, and I drew it as tension. That's why it gets a T. Okay, which indicates that it's a tension member. Okay, do the same thing on Fy. Okay, and we can have Fy equals 0, acting upwards positive. Okay, and so for this particular picture, I have my FBA, okay, minus my AY. That's the equation that we're writing to it. And then so 500 newtons minus 500 newtons equals 0. And it should, because, we knew the reaction was 500 on AY acting down. So if everything is in equilibrium, we've solved this, right? This thing better be equal to 0, so we know that it checks out for us on there. Now, you'll notice that I'm only using two equations, Fx and Fy, as we start to kind of look at these particular equations. And so what we want to make sure of is that, what happened to the sum of the moment equation? Well, because all of these forces are acting at the same point, and this was the same whether I was looking at this joint or this joint or this joint. If I sum moments at this point on this joint, every single force is acting through that point, right? So if we remember that moments is force times distance, the distance of this guy from the joint, the perpendicular distance that is 0. And same for him, and same for him, and same for him. So basically what's going to happen is on this, we could write sum of moments equals 0, go counterclockwise positive, and I basically get AX times 0 plus AY times 0 plus FBA times 0 plus FAC times 0. Okay, and then clearly that tells me that 0, and that better be equal to 0. Okay, well, that's a true statement, but it doesn't tell us a whole lot about what we're trying to find out. Okay, and that's what we can do on that. Now, to go into the method of joints, for joint C, okay, it's the same basic picture. Again, that's the picture that we saw that was happening up here. Okay, so FBC, FAC, CY, and we can write all our equations, and in a similar fashion, we can do our math. So it's very, very simple, and it's a very, very easy method. Okay, the problem is that I can only have no more than 2 unknowns at a time. Okay, so that kind of can start to create some problems. Okay, so if we look at what's happening, say, on another example, let's try this guy. Okay, and so this is a little bit more of a complex truss, and if we look at this, we can see we can set ourselves up that we have a 400 Newton force acting down, and we have a series of joints and connections. Now, if I draw the free body diagram, that's this real rough little sketch that's happening down here. I have CY, CX, and then I have these two forces. So when I do this joint on here, I'm going to have 4 unknowns. Okay, well, that's kind of a problem. Okay, if I come down and I do this one, I'm going to have 4 unknowns. Well, all right, so I can't start there. And so if I come down here, then I'm going to have 3 unknowns plus the known 400 kip load, and it's still a problem. And so even over here, I have 3 unknowns currently. That's why finding these support reactions first is so important, okay? Now, regardless of what happens, if you go through and you find AY, CX, and CY, I can write the equations here, okay? So if you want to pause the video, you can kind of work through this yourself, okay? And you can see that I have sum of forces X equals 0, 600 newtons minus CX, and I can see that CX is clearly 600 newtons acting to the left, okay? And if I slide this over a little bit so you guys can see the rest of this, okay, I can see that AY is 600 newtons acting up, okay, which is the reaction out here, and then CY is 200 newtons acting down. You guys can go through all of that and do that yourself. Okay, what I want to get to is I want to get to what happens to the joints. Okay, and so let's just go through and look at our particular equations. Now, suppose that you didn't know where you wanted to start, and you tried to start at this particular joint and went to joint D first. Okay, the free body diagram would look something like this. Now again, I've assumed this guy compression. Okay, I actually assumed FDC is compression, and I assume this guy is positive. Okay, and then 600 newtons acting to the right, so forth and so on. At the time that we start to analyze this truss, that's all of the information that you know. I don't know the value of that guy to the left at D. All right, and so that becomes a problem because with only 2 equations, sum of forces X and sum of forces Y, I can't possibly find all 3 unknowns. Okay, so that's why we got to start somewhere else, and I've got to find one of the others. So if we look at our particular path, you have to start somewhere where there are 2 unknowns, and in that case, that happens to be this joint A, right? So here's my free body diagram for A, and if I do this just like we did in that first example, and again, you can kind of pause it, I'll let you look at the equations on this, but AY is acting up, FAB is acting down, FAD is acting to the right. Okay, and so 600 minus 4/5 FAB is equal to 0. That's my Y equation. If I do that, I find out that FAB is a positive 750 in the math. That will be a positive value, and so the positive tells me this guy is drawn correctly. And so if he's drawn correctly, then he was drawn as compression, so clearly he's a compressive value. He's a member that's wanting to get shorter based off of the load. And then sum of forces X equals 0, force AD minus 3/5 times 750 equals 0, so forth. FAD is 450 newtons. And that guy has to be a tensile value as we look. Okay, once I do that, then I can come back down and I go, okay, well, I've got these 2 guys. So FAB and FAD are known. Well, when I go draw the other free body diagram at joint D, now I know him. Okay, and so he was drawn as tension here. He has to be drawn as tension here. If you flip one or change the equations for whatever reason, you have to update the other guy. Otherwise, you're going to get this all messed up. So when I do this, now I have this guy known, and I have the 600 newton. Now I'm down to 2 unknowns. This becomes a solvable system, just like all of the others. Okay, so there's this progression that starts to happen as we go through our approach. So if we do this, we can, again, pause the video, take a look at the equations that we've written. Sum of forces X is equal to 0. I can do minus 450 plus 3/5 FDB plus 600. All equal to 0. We'll find out FDB is a negative 250 newtons. All right, so here's where that problem is, because the math, the way I wrote the equation to the picture. And so if FDB is negative, that tells me that this guy is not the way that he's drawn. Okay, so I drew him as compression, okay, when in reality he's a tensile value. Okay, and so that would be the way that we start to look at it. So make sure you watch those positive and negative signs. So it's generally better practice, I think, to solve mathematically what it's doing and put the sign on it, and then write your answer on the next line in FDB and then add the C or T. You have to have this correct though, okay, because a minus 250 newtons tells me nothing, okay, if I just write that, because I'm going to go, well, are you looking at this member or are you looking up at his other end? Okay, so you've got to write it this way. It's very, very important. Okay, now doing sum of forces in the Y direction, we do the same thing, and you can run through all this. Again, we find out that FDC in our particular picture, again, we drew it as compression. If I solve this equation, you'll find out that FDC is a positive 200 newtons. All right, so this would tell me FDC is positive 200 newtons, and it's this positive that tells me the picture here is correct. So positive 200, positive drawn as compression, so that's why he's a compressive force. Okay, and we can kind of work our way through our system and do the rest of the truss that way, all right? Okay, now we can then jump up and get some of the other values. At this point, I know all of the other forces except for that 600 newtons, but if I write the free body diagram for joint C, which was here, here's my picture. So here's my CX reaction, my CY, which are known. Now these have to match what you saw back in the very beginning for the support reactions. Okay, and then FDC was the value that if I pull this down a little bit, FDC we said was 200 newtons in compression. Okay, so then I have to draw him as compression, and he's 200 newtons. Okay, and then FCB in this case is acting to the right, and I can solve for everything else. All right, and so the final solution to this truss looks something kind of like this. Okay, now one of the problems that I want to show you before we set up for the next free body diagram. Okay, for the next example, let me get a piece of paper out of here. Okay. All right, is what happens if you have a truss that looks something like this? You know, let me just draw this real quick. Let's just do simply supported. We'll put a point load out here in the middle somewhere. Okay, and if I just draw this as a basic Warren truss for what it is that we're trying to do, you get something that kind of looks like that. Let's just say this is 100 kips. Okay, we'll put them in the middle. This will make this as 50 kips. Okay, this becomes 50 kips. Let's just go A, B, C, D, E on here. I'll say that you want to find the force in member DE using the method of joints. You now see the problem with this, all right? Because I can't just jump out in the middle because every one of these nodes is 2 or more members, all right? So we have to start, assuming that we know that this guy is 0 kips, I have to start somewhere where there's only 2 unknowns. In this case, it's either A, okay, or it's out here, whatever the joint this is, F, G, H, I guess this would be I, okay, whatever the label is, okay. I would have to start here and work my way back, or I'd have to start here and work my way back. And the problem comes out if we just finish these out, J, K, L, M, N, O, P, Q, and R, all right. The progression would be then that you start at joint A, okay, on this, and then I would move up to joint R, and then I would move over to joint Q, and then I would move down to joint B, and then I would move over to joint C, okay, and then I would move over to joint P, and then I would move over to joint O, okay, and then I would move down to joint D, and at this point, now I've got one of the forces. When I draw D, this guy will show up. Now remember, for every joint that we just went through, we have to draw a free body diagram, and for every free body diagram, I have to write 2 equations. So that would be 1, 2, 3, 4, 5, 6, 7, 8 sets, okay, times 2 equations, okay, is 16 different equations you would have to have, okay, and that's our free body diagrams. You would have to write 16 equations, and in doing so, you'd have to do every one of them exactly right, never make a sign error, and it becomes a bit of a challenge, okay? This doesn't even calculate the issue that we have with numerical sensitivity. You know, if you have an error, a small error in a number, and I move to the next one and use that number, the error propagates through. Okay, even if things were perfect on this, that's still 16 equations, and it's 16 opportunities for you to screw something up. And I speak from personal experience. That happens to me. This is hard even for me to do without blowing a sign somewhere. Okay, so we want to try to come up with a better method than doing this. So method of joints is very simple, and it's very straightforward. It's 2 equations per free body diagram, and it's pretty handy if I'm trying to find something in the first 2 steps or something, okay, or if the structure is fairly simple. But if you're trying to get out into the middle of one of these really long, long trusses, that's a problem. And so we need a better way. And that will lead us into our next discussion, which will be known as the method of sections. So if you guys will stay tuned for that one, I'll kind of work us through that as well. So hope that makes sense. Thanks.